Hi, my name is Akshay and this is Half Sleeves.
In this explanation, I would assume that you have fundamental understanding of linear algebra. So, if you don't know the concepts like linear transformation, eigenvectors, eigenvalues, and bases, and etc., I would recommend you to watch the linear algebra video series from 3 Blue 1 Brown. In the last video, we saw that GANs are just trying to minimize and maximize a function and find a minimax point through these equations. Let's change the role of x and y and assume that x is minimizing the function and y is maximizing the function. The reason for that will be clear later. So, x is minimizing the function, which means it is moving in the downward direction or it is in the descent. And y is maximizing the function and it is in the ascent. That is why this process of finding the minimax point by ascending and descending with the help of gradients is called gradient descent ascent. And we use this rule of gradient descent ascent to find our minimax point and train our GAN. Here they find the minimax point when they add or subtract small portion of the gradient from the current position x0 y0 to reach to the next point x0 plus 1 y0 plus 1, which is closer to the minimax point, and then we can use this point x0 plus 1 y0 plus 1 to find the next point x0 plus 2 y0 plus 2, which is closer to the minimax point than x0 plus 1 y0 plus 1. We keep iterating through these equations or keep repeating the same operations again and again so that we can get closer and closer or get to that minimum maximum point, or if we repeat this process k times, these equations would generalize for k points, giving us x naught plus k and y naught plus k and converge to that minimax point or will reach very close to the minimax point, because remember, our main aim is to get to that minimax point. And these operations we are doing are specifically designed to converge to that minimax point. So we are basically iterating through the equation or repeating the same operations again and again. Now looking at the equations, we can get only a limited idea of what is going on. And to get a deep analysis, we need to convert these operations to linear algebra. Again, if you are not familiar with basics of linear algebra, please watch 3 Blue 1 Brown's linear algebra lecture series, because there's going to be a lot of linear algebra here. Let's choose a function fxy and see how these calculations pan out. This is the function we will choose. fxy is equal to minus 3x square minus y square plus 4xy. This would be the gradient of our function with respect to x, and this would be the gradient of our function with respect to y. Putting the value of these gradients in the above gradient descent ascent equations would result in these equations. We can take the common variables out and rewrite the equations. Now notice that these system of equations are linear, so we can write these system of equations as a linear transformation. These equations will be converted to a linear transformation like this. This linear transformation on the right is same as the operations in these equations. Now, after the transformation, we have got these new points x naught plus 1, y naught plus 1. And we can use these points to go to the next point, just like we did in the equations. Only difference would be that this time we would use the transform. So now we just apply the transformation again, but this time on x naught plus 1, y naught plus 1, and we get x naught plus 2, y naught plus 2. When we put the value of x naught plus 1, y naught plus 1 from this previous equation in the new equation, we get this equation. Now, since the transform is multiplied 2 times, we can also write it as raised to the power of 2. So this shows that performing the transformation or repeating the operation in the equation twice is just the same as multiplying the input vector with the transformation raised to the power of 2. Which means repeating operation is equivalent to multiplying it with a matrix with a power. And this can be generalized for k steps rather than just 2 steps. And then if it is generalized for k steps, we get x0 plus k and y0 plus k, because we want to reach to that minimax point. So we will be performing this repeating operations many times, or k times. Let's look at the graph of this function. The minimax point of this graph is 0, 0. The minimax point of this graph is 0, 0. But after k iterations, we are also trying to reach the minimax point, which means that the point or the vector x0 plus k, y0 plus k obtained after the kth power of the matrix should be 0, 0, or it should be the minimax point, because that's where we want to go. So we want the system to output 0 vector, or transform the input vectors to 0 vector, or x0 plus k, y0 plus k vector to be a 0 vector. When will this system output 0 vector, or the input vectors x0, y0 will become a 0 vector? We will get a 0 vector when each element of the input vector x0, y0 gets multiplied to a very small number. Multiplying each element of the vector with a very small number is just like multiplying the vector with a matrix which has small numbers as the diagonal of the matrix, and everything else in that matrix is 0. Now we can compare these two transformation equations as they are equivalent. When we compare them, we find that the matrix raised to the power k will have to be such a matrix which has very small numbers as their diagonals, very small number meaning close to 0, and everything else has to be 0, exactly 0. I have taken the negative powers of 10 just to show that the diagonal of the matrix will have very small numbers. So for generalization, let's replace the negative powers of 10 with a variable vs. Vs just shows that the value is very small and near 0. We can take the kth root of both the sides and get this matrix with 1 by kth power. This 1 by kth power can be transferred inside the matrix to each value of the matrix, like this. We know that this 1 by kth power can be transferred inside the matrix to each diagonal value like this. We know that Vs is very small and close to 0. So as k gets larger and tends to infinity, this Vs raised to the power 1 by k will approach 1. Which means Vs raised to the power 1 by k will be between 0 and 1. Or all the elements in the diagonal of the matrix would have to be between 0 and 1, where x and y are between 0 and 1. So we need to convert this transform on the left to this transform on the right with diagonal values between 0 and 1, so that when we apply this transform raised to the power k on our input vector, the output is the minimax point or the vector 0, 0. Now it turns out that all the transform can be converted to this form, given that we are doing the calculations on a computer. Now I'm going to explain how most of the matrix can be converted to this form if we are calculating on a computer, through a process which is called the diagonalization of a matrix. Knowing this process would help you understand the problem with GANs in depth. But if you already know what is diagonalization of a matrix, you can move to the next section. Again, content further in this video assumes that you have understanding of basic linear algebra. So if you do not know that, please watch 3 Blue 1 from series on linear algebra, as I said earlier. Let's say you have a transformation 3, 0, 2, 1. This is how this transformation looks. Here there are 3 points. Red point at 0, 3, purple point at 1, 3, and blue point at 2, 3. Observe that the distance between the red and the purple dot is equal to the distance between the purple and the blue dot. If you look at this animation of linear transformation, you would observe that after the transformation, still the distance between the red and the purple dot is equal to the distance between the purple and the blue dot. So before and after the transformation, both the distances are equal. It's just that after the transformation, the distance is just scaled up. And the same is true for transformation on x-axis. Just that in case of x-axis, the scaling factor would be 1. Which means that a transformation just scales the y and x distances. And you can take any 3 dots on x and y axis, which means it scales all the y and x equally. By the way, the dashed blue dots are the original bases. This is very important, that a transformation scales all the y and x equally, because that means if you apply transform on two different vectors, their x and y will be scaled or transformed by same factor. Now let's check our proposition by applying the transformation on two different vectors and see if the x and y are scaled by the same factors p and q each time. Let's test it on 2, 2 and 3, 1 and apply the transform on these two vectors. But here x and y seems to change or get scaled by random factors. In case of 2, 2, it gets scaled by factors 3 and 3. And in case of vector 3, 1, it gets scaled by factors 3 and 1. The factors for these two cases are different, but our aim is to make them similar. Actually, the problem is the basis, and if we change the basis, we will get constant factors for all the vectors. How a change in the basis solves a problem will become completely clear in a while. You know that every vector can be written as the linear combination of the bases. Our bases are 0, 1, which is here, and 1, 0, which is here. So we can represent the vector 2, 2 as a linear combination of these bases. This part is equivalent to traveling 2 units on x-axis and reach here, while this part is equivalent to traveling 2 units on y-axis and reach here. So we will reach the point of the vector 2, 2. Now let's change the basis to 2, 0, which is here, and 0, 2, which is here. So we can represent the same vector 2, 2 as linear combination of the new bases. This part is equivalent to traveling 1 unit on x-axis and reach here. But remember that our new 1 unit is 2, 0. And this part is equivalent to traveling 1 unit on y-axis and reach here. So we will reach the point or vector 2, 2. So if you look at the factors with these previous bases, the factors are 2 and 2. And the factors with new bases are 1 and 1. So we have changed the factors by changing the bases. So we can change these factors too by changing the bases. By the way, this vector can be written as the linear combination of its bases like this. This is our transformation, and these are the eigenvectors to this transformation. These eigenvectors of our transformation are linearly independent, because one cannot be created by the scalar combination of the other. Remember that to be a basis, only linear independence is required. So these eigenvectors can be the basis of our vector space. So instead, let's make the eigenvectors our bases, and let's see if this change of basis can help us get some constant factors each time we apply transformation. These are our original basis vectors, and these are the eigenvectors of our transformation, which we will make our new basis. Now we will convert the vectors and the transform from the original basis to the new eigenvector basis. Let's consider the vector 2, 2 in the original basis. This vector will be represented by the vector 2, 0 in the new basis. Let's see how. Remember that the dotted blue lines represent the old basis. The vector 2, 2 can be represented by the purple cross shown here according to the blue dotted lines. Now let's see how you can reach to this purple cross. This is our y basis and this is our x basis. To reach the purple cross, we need to move 2 units in the x direction and 2 units in the y direction. Now let's see how you can reach this purple cross with the help of new eigenvector bases. Our first new eigenbasis 1, 1 is shown here in red dots. And the second new eigenbasis 0, 1 is shown here in green dots. To reach the purple cross, you need to travel 2 units along the bases 1, 1, shown here in the red dot, and you will reach there. You don't need to move any units in y directions, so the distance covered in the y direction will be 0. So to reach the vector 2, 2 in new basis, you need to move 2 units in x direction and 0 units in y direction. And 2, 0 is the vector which represents 2, 2 in the new basis. Actually, 2, 0 and 2, 2 are same vectors. It's just they are seen in different measuring units. Now, when the transform is applied on 2, 2, we get a vector 6, 6. Vector 6, 6 in the new basis will be represented by the vector 6, 0. The dotted blue line represents the old basis. The vector 6, 6 can be represented by the purple cross shown here with respect to the blue dotted line or the old basis. Now to reach the purple cross with the help of new eigenvector basis, you need to travel 6 units along the basis 1, 1 shown here in the red dot, and you will reach there and the distance covered in the y direction will be 0. So 6, 6 in the new basis will be represented by the vector 6, 0. When we change the basis, the transformation will also change due to the change in basis. But this new transformation will transform the vectors exactly the same way as the old transform. So let's call this new transformation in the new basis as capital T. We will get to know the exact value of this transform capital T later on. So what we have done is converted these vectors and this transform for the new basis. Let's take another example and let's take the vector 1, 3. The dotted blue lines represent the old basis. The vectors 1, 3 can be represented by the purple cross shown here with respect to the blue dotted line or the old basis. Now to reach the purple cross with the help of new eigenvector basis, you need to travel 1 unit along the basis 1, 1 shown here in the red dots and travel 2 units along the basis 0, 1 shown here in green dots. So 1, 3 will be represented by the vector 1, 2 in the new basis. Now when the transform is applied on 1, 3, we get the vector 3, 5. The vector 3, 5 in the new basis will be represented by the vector 3, 2. The dotted blue lines represent the old basis. The vector 3, 5 can be represented by the purple cross shown here with respect to the blue dotted line. Now to reach the purple cross with the help of new eigenvector basis, you need to travel 3 units along the basis 1, 1 shown here in the red dots and travel 2 units along the basis 0, 1 shown here in the green dots. So the vector 3, 5 will be represented by the vector 3, 2 in the new basis. Now when the transform is applied on the vector 1, 3, we get vector 3, 5. Vector 3, 5 in the new basis will be represented by the vector 3, 2, which means that when we apply the transform capital T to 1, 2, we get 3, 2. Similarly, the vector 2, 5 will be converted to 2, 3. Then the transform is applied on the vector 2, 5 and we get vector 6, 9. Vector 6, 9 in the new basis will be represented by the vector 6, 3, which means that when we apply the transform capital T to 2, 3, we get 6, 3. Again, similarly, the vector 4, 6 will be converted to 4, 2. Then the transform is applied on 4, 6, we get vector 12, 14. 12, 14 in the new basis will be represented by the vector 12, 2, which means that when we apply the transform capital T to 4, 2, we get 12, 2. Now let's look at the constant factors which we get after transformation in each basis. In the original basis, when the vector 2, 2 is transformed to 6, 6, 2, 2 gets scaled by constant factors 3, 3. When the vector 1, 3 is transformed to the vector 3, 5, the vector 1, 3 gets scaled by constant factors 3 and 1.3. When the vector 2, 5 is transformed to the vector 6, 9, the vector 2, 5 gets scaled by the constant factors 3 and 1.8. When the vector 4, 6 is transformed to the vector 12, 14, the vector 4, 6 gets scaled by the constant factors 3 and 2.3. So we see in our original basis, different vectors after transformation are scaled by different constant factors. In the new eigenvector basis, when the vector 2, 0 is transformed to the vector 6, 0, the vector 2, 2 gets scaled by the constant factors 3 and 1. When the vector 1, 2 is transformed to the vector 3, 2, the vector 1, 2 gets scaled by constant factors 3 and 1. When the vector 2, 3 is transformed to the vector 6, 3, the vector 2, 3 gets scaled by the constant factors 3 and 1. And when the vector 4, 2 is transformed to the vector 12, 2, the vector 4, 2 gets scaled by the constant factors 3 and 1. So we see in a new eigenvector basis, different vectors after transformation are scaled by the same constant factors 3 and 1, which is all we wanted. So the transformation capital T in the new eigenvector basis always results in scaling the vectors by 3 and 1. But scaling a vector by 3 in the x coordinate and by 1 in y coordinate is equivalent to multiplying the vector by this matrix, which means this matrix is the transformation capital T which we are looking for. So when we change the basis to the new eigenvector basis, the original transform is converted to this transform, which scales every vector with constant factors every time. And these constant scaling factors 3 and 1 are the eigenvalues of the respective eigenvectors. You can understand this with an example. First, these are our new bases. Next, let's take a vector 1, 3. And as you know, we can write this vector as the linear combination of the bases. This is our original transform. Then we apply this new transform to the vector 1, 3. The vector 1, 3 can be written as this. So applying the transform is equivalent to applying the transform to the linear combination of the bases. But our bases are the eigenvectors. And applying this transform on the eigenvector is equal to scaling the eigenvector with the eigenvalue. So this equation can be written like this. And thus the vector is scaled by 3 and 1 on x and y coordinates. And the important thing is you can do this for any vector a, b. So for this transformation, we found another equivalent transformation which has all the values 0 except for the diagonal values. And the diagonal values are eigenvalues. If you go ahead and calculate the eigenvectors of this transformation, you will find that this transformation has only one linearly independent eigenvector, and that's why it can't be the basis of the vector space. Thus, this transform cannot be converted to the above diagonal form with eigenvalues in the diagonal. Transforms which cannot be converted to the diagonal form are called as non-diagonalizable transforms. But if you remember, I said earlier that all of the transformation can be converted to this diagonal form if we are doing the calculation on the computer. Well, doing the calculation on the computer means that we don't take the exact values of the real number, and to save the computational cost, we round off the figures to around 7th or 8th decimal places. And the interesting fact about non-diagonalizable transforms is that they are very sensitive, and even if one of the values of the transform are changed by even 1 billionth, the transform would become diagonalizable and will have two linearly independent vectors. Our current transform has only one linearly independent eigenvector. So let's say v is a very small number, let it be equal to 10 to the power minus 12, and we subtract v from the upper left value of our transform. Then our transform will have two linearly independent eigenvectors. Let's say the value of the upper left element of the transform is this. This value is exact up to 12 decimals. Now, since we are working on a computer, to save the computational cost, the computer will round off this value as this. This rounded off value is exact till 8 digit. So the error or the difference between these values will be of the order 10 to the power minus 9. 10 to the power minus 9 is obviously greater than 10 to the power minus 12, which means that if the upper left value is changed by anything greater than 10 to the power minus 12, it will convert to a diagonalizable transform. And since almost all the calculations on a computer have errors bigger than 10 to the power minus 12, all the computer calculations of this transform will be diagonalizable. For this transform, these two will be the complex eigenvalues if the upper left element has a difference of 10 to the power minus 12. So the equivalent transform when we change the basis to the eigenvectors would be this transform. But we are going to apply this transform on the input vector x0, y0, k times. So we can write it like this. But since this is a diagonal matrix with all the values 0 except for the diagonal values, we can write the power as this. The modulus of these complex numbers is greater than 1. So when raised to the power k, assuming that k is large, they will become larger and larger because their modulus is greater than 1. And thus, the output vector x naught plus k and y naught plus k will also be very large and much greater than 1. So the minimax point is at 0, 0. And we found that this GAN will never converge to 0, 0. In fact, we found that it will diverge further and further. So we just showed with this example that in this case the GAN will not converge to this minimax point through the process of gradient descent ascent. So what does that mean? This is the equation of the loss function. So did we just show that for this loss function this GAN will never converge? Did we show that? No, we did not show that. In fact, instead of x being the minimizing and y being the maximizing player, if x is maximizing the function and y is minimizing the function, then this transform made by the gradient descent ascent of this function would have two linearly independent eigenvectors, which have eigenvalues smaller than 1, and it will converge to 0, 0. Which means that what we have shown is that gradient descent ascent for GANs are not reliable and can converge for some cases and won't converge in some cases. In fact, GANs don't converge in almost all the cases using gradient descent ascent. And that is why the main problem with GANs is that they don't always converge to minimax point and they are so hard to train. They're so hard to train because they are so sensitive to smallest of the changes. And whenever I say GANs, I always mean that they are trained by gradient descent ascent. Because you may think that you use Adam, Adagrad, RMS prop and not GDA or gradient descent ascent for GAN training, but GANs are almost always trained by using gradient descent ascent, and all these other optimizers just provide additional support for the convergence, but the base is almost always GDA or gradient descent ascent. The main reason for all these problems is that eigenvalues are greater than 1, and this is due to the fact that the two players are trying to achieve contradictory and different objectives without any communication between them. One is trying to minimize the objective and the other is trying to maximize it. But while doing so, there's nothing common in them, which means there's nothing there which forces them to minimize and maximize the loss functions in such a way while keeping the weights and the parameters of the other function in mind, which also means that they are trained in a completely different spaces and they can adapt different strategies to reach to the minimum, meaning that they can update their weights in completely different ways to achieve their respective tasks. So there's no communication between the two networks, and one would take the steps in a manner that the other is completely unaware of those steps. So if they are unaware and can't communicate with each other, then one does not know what the other is doing, which means they only care about doing their own task alone and not for the collective good. So imagine if one of the network adopts a strategy to do its task which stops the other network to do its task. And that's exactly what happens here. This is the graph of our function. Let's say these are x and y axes. Let's first maximize this function over y. This method of maximizing and minimizing and finding the minimax point was shown in the first video of the video series. We will cut this function at each value of x and then maximize the parabolas obtained. Then we will join the maximum points and we will get a parabola. This blue parabola is often called the ridge of the graph. We will minimize this blue parabola to get the minimax point. But the overall process looks like this. We first find the ridge, which is this blue parabola line, and then move along the ridge or the blue parabola line to minimize it. We find the ridge by maximizing the function over y, which means that to find the minimax point, one must reach as close to this blue ridge as possible, and once we are near that ridge, we minimize the function along the ridge or this blue parabola. So let's say we start at this point, and then from here, if we maximize the function over y or try to get near the ridge, it would look something like this. And we will be moving in this direction on y-axis. Now we want to minimize the function over x according to the gradient descent ascent. When we minimize this function over x, we move in this direction on the x-axis and this direction on the graph surface. But we wanted to get as close as possible to the ridge. And to be honest, we were moving closer towards the ridge when we were maximizing the function over y. But when we minimize the function over x, we should have moved towards the ridge or the blue parabola, but instead we moved away from the ridge. Which means that one of the player which is minimizing the function over x is pushing the system away from the ridge or away from the minimax point. And one of the player which is maximizing the function is pulling the system towards the ridge or towards the minimax point. And this happens because there's no communication between the two players, due to which both of them are just acting to achieve their own goal rather than looking to achieve the collective goal. The X player is looking to achieve just its own goal, and that's why it moves in this direction. But what should have happened was the X player should have known that the collective or the overall goal is to move towards the ridge, so it should have moved approximately or somewhat in this direction. So this is the reason why gradient descent ascent does not work and GANs are so hard to train. As I told, the main reason for the problems with GANs is the lack of communication between the critic and the generator or the two players. So in the next video, I will explain a very nice method of establishing that communication between the two players.